In this video, I want to discuss Taylor polynomials, in particular the definition of a Taylor polynomial and the motivation for Taylor polynomials. We start with the following problem. We are given some function f, and for simplicity's sake, let's say f is defined on the whole real line. We also have some real number a, and at a we have a lot of information about the function f. We know the value of f at a, the value of the derivative of f at a, second derivative, third derivative, fourth derivative, and so on. Now, for some real number x near a, we want to approximate the value of f at x. So we want to approximate f of x. Now, this may seem a frivolous exercise because we are used to functions as things given by formulas. And if we want to calculate the value of a function for some specific value of x, we just plug in that value for x into our calculator and out pops an answer. But there is something that we should be wary of. Let's look at a simple example. Let's take the function f of x as cosine x, and we let a be 0. Now, it's easy to compute the values of f and its derivatives at 0. In particular, f at 0 is 1, first derivative of f at 0 is 0, the second derivative is minus 1, the third derivative is 0, fourth derivative is 1, fifth derivative 0, sixth derivative minus 1, seventh derivative 0, and so we carry on. The pattern continues ad infinitum. Now I ask you, what is f at pi over 4? Now don't laugh. You think, well, f at pi over 4 is just cosine pi over 4, and we know what that is. That is 1 over root 2. No problem. Right? Well, there is a problem. Remember, root 2 is not a rational number. It is irrational. Right? That means its decimal expansion is infinite. And it doesn't repeat. So if you plug root 2 into your calculator, right, root 2, it's going to give you an answer. 1.414213, and so on. Right? But be careful. This is in fact not equal to root 2. This is just an approximation for root 2. Remember, root 2, this symbol I've written down over there, is just a symbol that we use to denote the unique positive real number whose square is 2. Right? We can never know exactly what it is, because this decimal expansion carries on forever and ever and ever, and there's no recurring pattern. Right? So there's no point at which you say, okay, here we stop, and now the whole thing just carries on over again. We can never know what root 2 is. At best, we can find very accurate approximations for something like root 2. And Taylor polynomials is one way of doing this. So, back to our problem. Well, let's start with the simplest possibility. We try to approximate our function f using a straight line. That's the simplest non-constant, simplest function we have. Now, it seems reasonable to assume that at a our approximation is exact. In other words, L of a is equal to f of a. So the approximation is exact. Right? Geometrically, that means that the line y as L of x passes through the point a f of a. Right. Now what does this tell us about the line or the function L of x? Well, we want f of a to be equal to L of a, and L of a is ma plus c, and from this we deduce that we can express c as fa minus ma. And if we plug this back into the formula for L of x, we see we get m x minus a plus f of a. Right. Now, remember, our straight line is supposed to be an approximation for f. Now, how do we measure how good this approximation is? Now, this is a relevant question because there are infinitely many straight lines through the point a, f of a, and we need to know which one to pick that will give us the best approximation. Well, for that, we look at the relative error, this thing here, right? So what does this tell us? Well, if we look at the different terms here, we've got f of x minus L of x, right? That just tells us how far off is our approximation. So if the actual function value, say, is 1.5 and L gives us 1.25, then we're 0.25 off. But it doesn't make sense to think that the straight line through the point a, f of a, will give you a good approximation when x is far away from a. But we should expect that the closer we get to a, the better the approximation gets. And in fact, that's what this term in the divisor is there for, right? That's the difference between x and a. So that tells you how far is x away from a. Right? So the relative error, r of x, tells you relative to the distance between x and a, how good is the approximation f of x approximated by L of x. Right. So how good is our approximation relative to the distance between x and a, right? So if this guy is small, and likewise our relative error is small, that tells us that the approximation is good. Right. Now, in fact, we want this approximation to be very good as we take x close to a. So we require the limit of the relative error to be 0 as x goes to a. So in other words, our error becomes negligible relative to the distance between x and a as the distance between x and a becomes small. Now, what is our relative error? It is, per definition, absolute value f of x minus L of x over x minus a. Right, and now we know we've got here, we've got f of x minus minus m x minus a minus f at a all over x minus a. And this in turn, if we just rearrange a little, gives us f of x minus f of a over x minus a minus m. Now, we know what this term does as x goes to a, right? The limit as x goes to a, f of x minus f of a over x minus a is the derivative of f at a. Right. So from this we see that the limit as x goes to a of the relative error is 0 if and only if m is the derivative of f at a. So in other words, L of x must be f prime a x minus a plus f of a. And this we should recognize. This is just the tangent line to the curve. Y is f of x at the point x equals a, y is f of a. Right? And here we've got a sketch. Right? So here we've got the curve y is f of x, and here we've drawn the tangent line. And we see there's a, you can read off, there's f of a. Now, if we read off the graph, then we see here we've got f of x, that's the exact value. Right? If we go up a little, we read again off the graph, then we see there we've got L of x. Right? Right? So approximately equal to L of x. Right. Now, this is very good for approximating function values. But in some cases, we are interested not only in the function values, but also in how the function values change. Right? That means we are interested in the derivative. Because remember, the derivative gives you the rate of change in f. So for dealing with rate of change, in other words, the derivative, the straight line we had before is not good enough anymore. So we have to go up a level of complexity. Right? So we go to the next simplest function, and that is a quadratic. Right? So now, again, we want to approximate our function f of x, this time using a quadratic. Right? And we write our quadratic in this form. A x minus a squared plus b x minus a plus c. But this quadratic is not only supposed to approximate the function, we also want to approximate the derivative of the function, in other words, the rate of change. And we want to approximate that using the derivative of our quadratic. Right? And the derivative of the quadratic would be 2a x minus a plus b. And again, this approximation should be good for x near a. Now, what requirements should be put on this quadratic in order for this to be a sensible exercise? Well, again, q of a equal f of a. Right? So that means at x equals a, the approximation is exact. We get the exact value for f using our approximation when we set x equal to a. And now, second, we want these approximations to be good. So again, if we think of the approximation f of x is approximated by the quadratic q, then we have to look at this relative error. Right? This is the same relative error we had before, except now we have instead of a linear function. And lastly, we require the derivative of our quadratic to also be a good approximation for the derivative of f for x near a. So again, we look at a relative error. So now this time, it's the relative error for this approximation, right? So again, this is a distinguished from the previous one. And we want both of these things, these limits, to be 0. This limit being 0 says that for x near a, f of x is a good approximation for q of x. And the second limit being 0 tells us that for x near a, q prime of x is a good approximation for f prime of x. Right. Now let's see, what does this q have to look like? Well, we want q of a to be f of a. Now, q of a is a minus a squared plus b, a minus a plus c. And this is supposed to be f of a. Right. Now, that's 0, that's 0. So all that's left to see. So we see that q of a is f of a gives us c is f of a. Right. So we've got a bit more information about our quadratic. Right. We've got the constant term here being f of a. Now, let's see. Now let's look at the approximation f of x approximately q of x. Right? Again, we want this approximation to be good, which means this limit here should be 0. Now, what is this f of x minus q of x over x minus a? X minus a, x minus a squared plus b x minus a plus f at a over x minus a. Right? And rearranging a little, we get f of x minus f of a over x minus a x minus a okay. The signs are wrong there. Minus, and then there we have a minus again. Right. So f of x minus q of x over x minus a is f of x minus a squared minus b x minus a minus f of a. We rearrange and simplify, and we get f of x minus f of a over x minus a x minus a minus b. And now again, we know what this limit is. Right? Limit x goes to a, f of x minus f of a over x minus a. That's the derivative of f at a. And we know what the limit as x goes to a of x minus a is. It's 0. So that means the limit of this relative error, limit x goes to a, absolute value f of x minus q of x over x minus a. This is going to be 0 if and only if b is the derivative of f at a. Right. So we've got a little bit more information about our quadratic q. Right. We've got the coefficient for x minus a, and we've got the constant term there. Now let's see. Now we move on to the derivative. Remember, we require this limit to be 0, right? Because this tells us that the approximation derivative of f at x approximately derivative of q at x is good. Now, let's see. What does this look like? We've got f prime x minus q prime x over x minus a minus 2a x minus a minus derivative of f at a all over x minus a, and we rearrange a little, and we've got f prime x minus f prime a over x minus a minus 2a. Right, and now again, we remember, well, what is this limit? This limit, x goes to a of f prime x minus f prime a over x minus a. That's just the second derivative of f at a. So we can conclude that the limit as x goes to a of our relative error for the derivative f prime x minus q prime x over x minus a is 0 if and only if a is 1/2 second derivative of f at a. And that completely determines q. Right? We now know exactly what Q is. Right? We've got the constant term there, coefficient, and we've got that coefficient. Right. So this is exactly the second degree polynomial, or in other words the quadratic, that gives an exact value for f at a, and which gives good approximations for both f and its derivative for x near a. Now note that f of a is q of a, as mentioned, and also the derivative of q at a is equal to the derivative of f at a, and likewise the second derivative of q at a is equal to the second derivative of f at a. And this tells us that the graph of f and the graph of q have the same shape near a. Right? This first condition, f of a is q of a, that tells us that the derivatives of a function determine the shape of its graph. The first derivative gives you the slope. The second derivative tells you whether the graph is concave, up or down. In other words, is your graph opening up towards the top or towards the bottom? Right? So f and q will have graphs with exactly this, well, with very, very similar shapes near a. Here I've plotted the graph of the function f of x is cos x in red, and in blue we have the quadratic q of x, where we've taken a to be 0, and in this case it is 1 minus x squared over 2. And as you can see, for x near 0, the two graphs look almost identical. Right. So if we just look, say, between minus a half and a half, on the picture you can barely tell the difference between the two graphs. Right. So this quadratic gives us a good approximation for the function near the point a, in this case a equals 0, and the graphs have the same shape near a. Now we can take this further and ask that we approximate f with a polynomial so that not only the function and its derivative are approximated well, but also the second, the third, the fourth, the fifth, and so on derivatives. And this leads us to the concept of a Taylor polynomial. So what do we have here? We have a function f, and this function is defined on an open interval containing the real number a, and we have some natural number n, and we assume that f is n times differentiable at a. So that means the first derivative of f at a exists, the second derivative exists, the third derivative exists, the fourth derivative, and so on up to the nth derivative. Then we can write down what we call the nth Taylor polynomial for f about a. And this is just the polynomial written down here. Right? So take a moment and look at this formula. Right? We've got f of a here. Right? Then we have derivative of f at a times x minus a. So up to here, this bit here, we've just got the tangent line. Now if we look at our second degree term, now we're adding second derivative of f at a over 2 factorial. Remember, 2 factorial is just 2. So if we now add this term, now we've just got our quadratic q of x that we discussed a moment ago. Right? Now we add similar terms for the third derivative, fourth derivative, fifth derivative, up to the nth derivative. Right? Now let's look at a few things. Firstly, a compact notation. Right, so we can write the Taylor polynomial in this form. Right, so f of a, and then we add all the derivatives from first order up to nth order. Remember, k factorial is just 1 times 2 times 3 up to k. Right. Now, why do we define the Taylor polynomial in this way? Well, let's look at the derivative of the Taylor polynomial. Right, so that's going to be d dx f at a right, and let's take out, this is a constant over k factorial d dx x minus a to the k. Right, so this gives us, well, d dx f of a is 0, because f of a is a constant, plus, right, well, if we look at what happens when k is 1, then we're going to have d dx of x minus a, and that's just 1. And we're going to have first derivative at a, plus, right, and now for the other terms, k from 2 to n, right, we still have fk of a over k factorial. Now we differentiate this, that gives us k x minus a to the k minus 1, which, if we simplify, gives us f prime at a plus the sum k equals 2 to n. Right, and notice now the k is going to cancel out with the k term down here in the factorial. So we're going to end up kth derivative at a x minus a to the k minus 1 over k minus 1 factorial. And now we see what is the value of the first derivative of the Taylor polynomial at a. Well, all of this here is going to be 0, right? Because we're going to have x minus a, which is 0. So all that's left is the first derivative of f at a. Likewise, we can calculate the second derivative for the Taylor polynomial. That's going to be second derivative a is equal to 3 n fk at a x minus a to the k minus 2 over k minus 2 factorial. Right? And then we see the second derivative of the Taylor polynomial at a is the second derivative of f at a. And we can do this for any order of derivative. So we'll have the jth derivative of the Taylor polynomial f at a plus the sum k is equal to j plus 1 to n fk at a x minus a to the k minus j over k minus j factorial. This is of course for j less than n minus 1 or equal to. And then from this we see the Taylor polynomial as jth derivative at a and this is for j from 1 up to n minus 1. And in fact, you can show that the nth derivative is also equal to the nth derivative of f. Now, we should also note that the Taylor polynomial is essentially the best polynomial approximation for the function near a, and in the following sense. So Pn x best nth degree polynomial approximation for f near a. Right, and what we mean by that is that if we take the limit x goes to a, and now we take a relative error between the jth derivative for f at x for the Taylor polynomial at x, so it's a relative error x minus a. This limit is 0, and this is for all j up to n minus 1, right? So the Taylor polynomial is the best nth degree polynomial approximation for f near a, in the sense that f and all its derivatives up to order n minus 1 are approximated very well by the Taylor polynomial and its derivatives for x near a.